All right, today we're diving into something that might just break your brain a little, in the best way possible. It's called homotopy type theory, and it's a revolutionary new way of thinking about the very foundations of math and logic. We're about to rethink what something as simple as the equals sign really means.
So first things first, I need you to just forget for a moment what you learned in high school algebra. We're all taught that A equals B is just a statement of fact. It's either true or it's false. End of story. But what if that's not the whole story? What if A equals B wasn't a static fact, but a dynamic connection? What if it was more like a journey?
And that question, right there, is the heart of homotopy type theory, or HOT for short. You see, it's this wild mashup of two totally different worlds. On one hand, you have the super rigid rules of logical type theory, the kind of stuff that computer science is built on. And on the other, you have the fluid, squishy world of homotopy theory, which is all about the geometry of shapes and how they can be stretched and deformed.
So to really wrap our heads around this, we need a whole new way of looking at things. HOT gives us this incredible analogy. Think of it like a dictionary for translating these abstract ideas from logic into a world of geometry that we can actually visualize.
Okay, so this is basically our Rosetta Stone for understanding HOT. On the left, we've got the logic concepts. A type, you can think of that as a category, like the type of all even numbers. In this new world, we're going to see that as a geometric space. Then a term, like the number 4, which belongs to that type, that's now a point living inside that space. And here's the kicker. The identity type, the very idea of a proof that two things are equal, that becomes something called a path space. And that is the key to everything.
All right, so remember that journey I was talking about? This is where it gets real. If we start thinking of our mathematical objects as points in a space, then the whole idea of proving they're equal just completely transforms.
So in HOT, the statement A equals B isn't just a yes or no question anymore. It becomes the type, the collection of all possible paths that you can draw from point A to point B. Any single proof that A equals B is one of those paths. It's not an abstract logical deduction anymore. It's a concrete, geometric thing you can almost trace with your finger.
And what's so cool about this is that it doesn't break the old rules of equality. It actually makes them way more intuitive. Think about it. Reflexivity, the idea that A always equals A, well, that's just a path that starts at a point and loops right back to itself. Easy. Symmetry. If A equals B, then B equals A. That just means any path you can walk one way, you can also walk back. And transitivity? If you have a path from A to B and another from B to C, you can just stick them together to get a path from A to C. The abstract rules suddenly become visual common sense.
But here is where things get really, really wild. Just like you can take different roads to get from one city to another, in HOT, there can be multiple, completely different paths between 2 points. This is a massive departure from classical math. It means there can be different proofs that A and B are equal. The way in which they are equal suddenly matters. Each path, each proof is its own unique piece of information.
So this whole idea, this rich, geometric way of seeing equality, it all builds up to one single, profound, and unbelievably powerful concept at the heart of homotopy type theory.
Yeah, everything we've talked about so far, types as spaces, proofs as paths, it's all been setting the stage for one central axiom. An axiom so powerful, it basically lets mathematicians say that if two things act the same, they are the same.
Okay, so before we get to the big reveal, we need one more piece of the puzzle. What does it mean for two types or spaces to be equivalent? You see it written with that squiggly equal sign. It basically means that two spaces, A and B, have the same structure. You can map every point in A to a point in B, and back again, without losing any information. It's like having a perfect translation between two languages.
Now, it's pretty easy to see how this works one way, right? If two types are truly 100% identical, the old-fashioned A equals B, then of course they're also equivalent. I mean, if they're literally the same thing, they have to have the same structure. That's the easy part.
But, and this is the million-dollar question, can we go in reverse? If we can prove that two things have the exact same structure, that they're equivalent, can we just go ahead and say they're identical? Can we just replace that squiggly equal sign with a straight one whenever we want?
The univalence axiom just steps in and says, yep, absolutely. In the words of the people who literally wrote the book on this stuff, identity is equivalent to equivalence. Just let that sink in for a second. It's a bold declaration that if it walks like a duck and quacks like a duck, it is a duck.
So what does that actually mean formally? The axiom states that the space of paths proving A and B are identical is itself equivalent to the space of functions proving they're just, well, equivalent. It elevates the idea of looking the same to the level of being the same. This creates an incredibly powerful new tool for doing math.
Okay, I know this is super abstract and mind-bending, but why should we care? What's the point of all this? Why are mathematicians and computer scientists so incredibly excited about it? Well, for one, this wasn't just some idea one person had in a vacuum. It's been this amazing collaborative effort that's just exploded over the last couple of decades. It started with sparks from people like Vladimir Voevodsky, and the name was coined by Steve Awady. But it really took off when researchers from all these different fields came together for a special year at the Institute for Advanced Study and literally wrote the foundational text together, the famous Hot Book. And the real-world applications, they are huge. Because this way of thinking is so geometric and intuitive, it's perfect for computers. It's leading to a new generation of proof assistants. That's software that can check massive, complicated mathematical proofs to make sure they're 100% correct. Think about verifying the code that flies airplanes or runs a power grid. And because proofs are paths, these systems don't just know that two things are equal. They know how and why. It's even inspiring entirely new programming languages built from the ground up on these ideas.
At the end of the day, that's the real magic here. By giving logic and math a physical shape, HotTant helps computers reason in a way that isn't just brutally logical, but is actually much closer to how our own human intuition works. It's building a bridge between the machine and the mind.
And that leaves us with one final, massive question. The univalence axiom is a completely new rule for the game of mathematics. So if we're really building a whole new foundation, a new operating system for logic itself, what kind of incredible new structures, what new ideas that we can't even dream of yet, are we about to discover?